In this video, we'll talk about first law of thermodynamics for a control volume. First law of thermodynamics is just conservation of energy equation. We already know for a closed system, as shown on top of the screen, without inlet or outlet, first law is very simple, which is Q minus W equal to delta E. Q is heat transfer, W is work, and E is total energy. Delta means change. An alternative to this equation is to divide every single term by time. Q over time is called heat transfer rate, so we put a dot on top of Q. W over time is called a W dot, that is power. And the right-hand side becomes dE over dt. So our question is, what will this equation change into when we start dealing with a control volume where there is an inlet or an outlet, or more than just one inlet or more than one outlet? We can start from the equation we already know for the closed system, which is Q heat transfer minus W. Right-hand side is delta E. Because even when we move on to the control volume, we will still have to deal with heat transfer. We will still have to deal with work. And then there will still be the change of total energy as shown in the right-hand side. But what has changed is for a control volume, you have an inlet and an outlet. At the inlet, mass keeps coming in. When mass comes in, it brings in energy. So we need to add the amount of energy brought in at the inlet. So plus capital EI. At the outlet, mass keeps leaving our system. So energy also leaves our system with the mass. So we need to subtract the amount of energy leaving from the exit. So we write down minus capital EE. So this is pretty much the equation for our control volume, but we're not at the final form of this equation yet. We need to rewrite this equation slightly. So first thing we do is to rewrite those two big E's. Q minus W plus capital EI. Capital E stands for total energy, and we know total energy has three components. They are kinetic energy, so 1 over 2 mVi squared, plus potential energy. Potential energy is mgz, and I give it a subscript to indicate this is at inlet, mi and zi. And then the third component within total energy is internal energy. Internal energy is equal to mass times specific internal energy. And again, we give it a subscript to indicate this is the inlet. And then we just need to repeat for EE. The sign before it is minus, and the capital E will just be the same thing. 1 over 2 mEVe squared plus mEgze plus mEue. And the right-hand side will be delta E. Next, what we do is to divide every single term by time. If we do that, Q becomes Q dot and W becomes W dot, and everything inside the parenthesis becomes 1 over 2. Mass over time becomes mass flow rate with the dot on top of it. And same thing happens to the two remaining terms, m dot I gzi plus m dot I ui. Same thing happens to the exit. Right-hand side becomes derivative capital E over dt. So now we're at a step closer to the final solution. And the next, we just need to focus on discussing what is this W dot. What is this W dot? Let's quickly sketch our diagram again. We have a piston cylinder assembly, but this time we have an inlet and outlet, unlike before. We choose everything within the cylinder as our system, and obviously this is a control volume because you have an inlet and outlet. Inlet we call number 1, outlet we call number 2. Okay, so now what is this W for our whole system? So this W, first of all, the piston will still be able to move up or down, which we call WCV. This term comes from the moving parts. In this case, the piston moves up and down, so it's going to contribute to work. However, what is different is now we also have to take into consideration the inlet and the outlet, because at the inlet, what is happening is the pressure is pushing the fluid into the control volume. To push something over a distance, that is work. So we need to add one more term to account for the work happening at the inlet. And then same thing happens at the outlet. At the outlet, the pressure pushes the fluid out of the control volume. And again, to push something over a distance, that is work. So we need to add one more term to account for the work at the exit. Okay, so now let's start from the inlet. We know work is force multiplied by distance, and force is F, distance is D. However, force can be written to pressure multiplied by area. So we're going to change force to pressure multiplied by area. And now let's give it a subscript to indicate this is the inlet. PI, which is the pressure of the inlet. AI is the cross-sectional area of the inlet. So this cross-sectional area is my AI. And D is the distance. We call it DI. And now let's determine the sign before this term. Should it be plus or should it be minus? At inlet, what is happening is you are pushing the control volume and you are pushing my system. Therefore, my system gets pushed. If my system gets pushed, that means my system consumes work. If a system consumes work, the work must be negative. And same thing happens to the outlet. At the outlet, the term will just be PAD again, but this time everything is at the exit, so give it a subscript E. And now we just need to determine what is the sign before that. What is happening at the exit is my control volume is pushing the fluid out of it. So if my control volume, the system pushes, then my control volume is the one to generate work. If the system generates work, the sign must be plus. So now we have accounted for all three sources of work for our W. And if you take a look at the equation on top of the screen in the red box, what we need is W dot. However, what we have right now is W. That means we just need to simply divide every single term by time. W over time is W dot, and in the right hand side, WCV over time will be called W dot CV. And minus PI AI. D is distance. What is distance over time? Distance over time is velocity, so we write VI. So same thing happens to the third term in the right hand side, PE, AE, and VE. VE is the velocity of the fluid at the exit. Okay, next what we do is a mathematical manipulation to the two terms in the right hand side. What we do is, first of all, we have PI, AI, and VI. And what we do is to multiply this whole term with density and then divide it by density. So equal sign is still true. Then we do the same thing for the last term in the right hand side. PE, AE, and then VE. Multiply by density at the exit divided by density at the exit. The reason we do that is rho VA. Rho VA is something different. Rho VA is equal to the definition of mass flow rate. So this equation can be simplified. And in addition, what we can do is density. Density is the inverse of specific volume. So we can rewrite both denominators into specific volume nu. Now this equation will be changed to W dot CV minus PI times M dot I times nu I. Third term will become PE M dot E times nu E. So now finally we have rewritten W dot. All we need to do next is to replace this W dot in our previous equation. This is the equation after we replace the W dot CV with the new solution. And now we can further simplify this equation. If we take a look, M dot I, M dot I, M dot I, M dot I, those four terms have M dot I in common. So we can combine them all together and take M dot I out of them. Same thing, M dot E, M dot E, M dot E, M dot E. Those four terms have M dot E in common. So we can take M dot E out of those four terms. And after we do this algebra, the equation will become. And now we can further simplify this equation because internal energy plus P nu, as we know it, is the definition of specific enthalpy. So the first two terms will become HI, and similarly, those two terms in the red box will just be enthalpy at the exit. So here is our final solution. If we have multiple inlets and multiple outlets, all we need to do is to sum up all the inlets and then sum up all the outlets. And this is our solution. First law of thermodynamics for a control volume.